Hello, welcome to Aerospace and Mechanical Lab 1. Today we're going to talk about uncertainty analysis, the theory of uncertainty analysis. But before talking about the theory, let's talk about how the attendance is actually taken for these recordings, the lab recordings and the lecture recordings. So essentially what happens is when you go to Blackboard right here, you're going to see these modules for each week. Like the first, we have the course introduction module and also the uncertainty analysis module, which is your first lab. If you click on it, you're going to see a couple of things posted. We already have the lecture notes posted and also the lab recording posted. To receive credit for the attendance, you just have to click on this and watch the recording.
Hey guys,
The recording for this lab is done by Samantha, who is uh, uh, the person in charge of this lab for the spring 2025. Okay, and in this module you're going to see everything you need for this lab. You're going to see the Friday quiz posted, you're going to see the lab instructions and the submission portal posted here as well. So whatever that needs to be done for this lab will be posted as, in this module on Blackboard. I have received a couple of emails about when to actually watch these lectures. You don't have to watch them on Mondays or Wednesdays. Um, it has to be done during the week before the actual lab, so or before the quiz. So essentially I'm going to come to a Blackboard and check the attendance, check whether you have watched these lectures on a Saturday before the week of the lab. This first lab is a little different because there's essentially uh, the Martin Luther King holiday, which means that we are not going to have any labs, any recordings, anything whatsoever during that week. So you have to watch this recording this week for the lab that will be done in 2 weeks, and you also have to take the quiz. I'll also send another email about this to make sure everything is clear for everyone. But let's get to the lecture. So today we are going to talk about statistics and how to do a statistical analysis. We will talk about determination of estimates and uncertainty. We will talk about uncertainty propagations, and we will talk about what actually needs to be done in the lab. Okay, what is data? Data is the information that has been collected from an experiment, simulation, or it can also be collected from a survey or an historical record. In this class, though, we only rely on experimental data and simulation data in Lab 2 specifically, in Lab Class 2 specifically. So the only thing that means data for us is the recordings you have in the lab, you make in the lab. Okay, but these recordings are going to be different from the actual data because of the lack of accuracy and lack of precision. So you have to keep in mind, you just have to know the difference between accuracy and precision. Accuracy essentially means that your data are closer to the actual measurement, the actual data. Your measurement is closer to the actual data. But precision means that your measurements are consistent. They don't really have a huge level of uncertainty. It is possible for us to reduce or increase the precision, reduce the uncertainty in our data. But it is somewhat impossible for us to know whether we are measuring the actual data or not. So the precision, in this course at least, is the goal. We want to reduce the uncertainty, or we want to analyze how much uncertainty we have in our data as much as possible. Okay, how should we do this? We essentially have to make a couple of measurements, as you will do in all of the labs, in most of the labs, throughout the semester and throughout the next semester where you take Lab 2, and you have to find an estimate, just one number that represents all of your measurements, and then you have to calculate the uncertainty of all of those measurements. So your measurement is going to be an estimate plus and minus an uncertainty. So we have to know how to calculate the estimate and how to calculate the uncertainty of our measurements separately. Okay, let's talk about the estimate first. So estimate is essentially the central tendency of your measurements. Let's say you have made all of these measurements. Your estimate of the data is the central tendency, so it lies somewhere here. But how do we calculate the central tendency of the data? There are many different methods. One is calculating the mean or arithmetic average of the data. Mean is essentially To calculate the mean, you have to add all of your data together and just divide it by the number of the data points you have. Let's say you make 5 measurements, just add the 5 measures together and divide everything by 5 to find the mean of your data, and that will be your estimate. In this course, we are only going to use mean as a representation of our estimates, but there are other ways to calculate the estimate of the data. One is median, which is the central value in a group of ordered data. One is mode, which is the most frequent value of the data. And one is the geometric mean. So essentially, instead of adding all of your data together and dividing them by the total number of data you have, you are going to multiply all your data together by each other and take the nth root of the data of your data. So what's the difference between all of these? Let's say I have all of these measurements. I have measured, doesn't really matter what we are measuring, but the value that is measured is 1, 1, 4 2s. Three times we have measured 9, and once we have measured 90. Arithmetic mean for these is going to be 14. See, so arithmetic mean is higher than the 9, which is not the best representation of this measurements, not the best central tendency of this measurements because of this huge outlier, 90, right? Median and mode here, central value of the data is 2, and the most frequent number measured is 2. Again, that is not the best representation of the central tendency of the data, but the geometric mean is going to give us 4.7 for the estimates, right? That's the best representation of the data, which is usually the case for geometric mean. But for our data, where we don't really have huge outliers, we usually use arithmetic means. In your calculations though, let's say you have a huge outlier, you can decide to use geometric mean instead of arithmetic mean, right? And if you didn't remember how to calculate any of these, you can just always come back to this slide and learn how to do the calculations for arithmetic mean or the geometric mean. Okay, so again, we do not see huge outliers. That because we do not deal with surveys and qualitative data, which means that the mode and median, that don't using mode and median doesn't really make sense for us. We have to use arithmetic mean. Again, if you decide to use geometric mean, that is also fine, but you just have to mention in your report why you have chosen to use the geometric mean for the calculation. Just to make sure we are all on the same page at this point, we are reviewing the statistical analysis because in experimental in experiments in general, we have to make more than one measurements, and when you make more than one measurement, you are going to need to represent your measurements as just one value and one uncertainty, one estimate and one uncertainty. We cannot just report all of the data. We have to have some sort of a representation. That's why we need to do a statistical analysis. Okay, so estimate, very clear, calculate the mean, we should be fine. The next part is to determine the uncertainty, and this is where we need to define the standard deviation and the standard error. The standard deviation essentially is a deviation from the arithmetic mean. Let's say your data, the central tendency of the data or the mean of the data is represented by x of m. The standard deviation is going to tell us how much the rest of the measurements deviate from this central tendency. Like for example, in this blue line, you see that the deviation from this central tendency is not that much, but the purple line tells us that the deviation is very high. So sigma for this blue line is going to be higher than the sigma for this purple line. So it's going to be higher than the sigma for this blue line for the blue measurements. You might ask, why are we presenting our measurements as a continuous line? That is a good question. You have to keep in mind, when you have 5 measurements, let's say I have one measurement that lies here, one measurement that lies here, one measurement that lies here, and two that lies here. They are I only can present them by just showing the points where the measurements lie on any axis, and I can only point out to the central tendency. These lines represents infinite number of measurements, and the theory is if you make an infinite number of measurements, your data will be presented like a bell curve or a normal distribution. That's why we have these bell curves here. So this is essentially assuming we have made infinite number of measurements, right? Which we never do, right? So this is just a theoretical representation of our data. But the formula we use for central deviation might change if you add more and more measurements. But you can use this formula for any number of measurements. The standard error, which is essentially the standard deviation of all of the means for a lot of measurements, you don't really need to go to the background of this, is calculated by dividing the standard deviation by the square root of number of data points you have. So you have made 5 measurements, this n is going to be equal to 5. Right? That is called the standard error. Okay? So uncertainty, the definition of uncertainty is the frequency with which a certain event occurs after a large number of tries. So the idea is I have calculated my mean, and my uncertainty is some value. That value is going to tell me the probability of one specific measurement happening that deviates from the mean. Do we need to understand this completely? No, not really. You don't really need to understand this for your calculations. I just wanted to make sure that we know that this exists. And the normal distribution that I mentioned, which is the infinite number of measurements, the distribution of infinite number of measurements, has this formula. This is the Kerr formula for the normal distribution. This is P of x, so probability of x happening, x is right here, can be calculated by this formula. Do we need to use this formula? Not at all, never. So if you have trouble understanding this, don't worry about it. Okay, how can we determine the uncertainty? The first thing you want to do is to choose the appropriate methodology. The methodology we are going to talk about here is called z-score, or the standardized standard normal distribution, right? And we don't really use this for all of our calculations. This is used usually for the cases where the number of measurements is higher than 25 or 30, right? We are going to introduce another method for the cases where the number of measurements, number of data recorded, is less than 25 or 30. Okay? So essentially what happens is you have to standardize your measurements to fit this description. Alright? So your mean has to become 0, which essentially means that you have to calculate the mean and you have to subtract all of your data points from the value of the mean. So the mean is 0 and everything is distributed from negative to positive. And then the standard deviation has to be, for that value, has to be 1. So you divide everything you have by your standard deviation. That's what happens. Again, you don't really need to do these things for your data. This has been done many times, and they have come up with a table, which essentially you just have to go to the table and choose an appropriate z-score. That's how you standardize your data. Okay. So what's going to happen? You make a couple of measurements. You calculate the central tendency. You calculate the standard deviation or a standard error. Doesn't really matter. And then you are given a confidence interval. You are given you are going to be told that I need to find the confidence interval for this confidence level, like 75%, 90%, whatever. And you find the appropriate z-score for that confidence level, you multiply your standard error by that z-score, and this is how you present your data. Or you can present them in a form of an actual interval. So your mean minus the z-score multiplied by the standard error or the standard deviation. Again, doesn't really matter which one you use, standard error or standard deviation. And this is the lower bound of your data. The higher bound of your data is your central tendency estimate, your arithmetic mean, plus the z-score multiplied by the standard deviation. Okay, so there are a couple of things we need to find the z-score. We already know how to calculate the standard deviation or standard error and the mean. We don't really know how to calculate the z-score. We know it in theory. This is what we need to do, but we don't really know it. We don't really know, like, practically what to do. Essentially, what you need to do is to go to these tables. The numbers you see here are your confidence interval. So all of these are values after the decimal point. So this is actually like, for example, this value here is 0.49520. This is essentially tell us that the confidence interval is 49%. Okay, so if you were told the confidence interval is 49%, you have to find this value in the table and then read the z-score using these two columns, like this one column and this one row. How to read the z-score? So this is 49%, your confidence interval. The z-score is 2.5, and then 9. So your z-score is 2.59. This is the hundredths after the decimal. This is the tenths after this decimal point. Z-score again, 49% confidence. Z-score is 2.59. Another example. Let's say your confidence level is 21%, or 0.021, 21.566%, right? Your z-score is going to be 0.57. Okay. But there's also one other thing that you have to keep in mind, that these tables represent half of the standard normal distribution. So this half, essentially the positive half, which essentially means our confidence level needs to be divided by half before reading the values from the table. So, like this, let's look at this value, 45%, for example, 45. This number represents a confidence interval of 45.45053 multiplied by 2. So essentially, this represents a confidence level of 90%. Okay, again, why is this the case? Essentially, the reason this is the case is because of the fact that the area under the curve of this standard normal curve is 1, representing 100% confidence. So 90% confidence means a portion of this curve, which area is 0.9 or 90%. Okay, so if you divide this by half, the area under the curve is going to be 0.45 or 45%. Okay. Again, if you have trouble understanding the background, doesn't really matter. What matters is to calculate the z-score, you have to divide the confidence level given to you by 2, and then come to this table, find the closest value to your confidence level, or do an interpolation, and then pick the appropriate or corresponding z-score. Okay, let's solve an example problem. Let's say we are told that assume a measurement has a normal distribution. We are not told the actual measurements, we are just only given the arithmetic mean and the standard deviation. So arithmetic mean is -4, the standard deviation is 5.2. We want to find the confidence interval in which 90% of the population lies, meaning that this is 90% confidence level. So just have to divide this by 2, 45% or 0.45. Come to this table, see 0.45, 053, 0.44, 902. So our confidence level lies between these two values. Just do an interpolation between the two z-score values. The z-score value for this one, 0.45053, is 1.65. So 1.65. For the other one, it's 1.64. Just have to do an interpolation. Which is going to give us 1.645 for z-score. Okay, so the lower bound of our data is -4 minus 1.64 multiplied by the standard deviation. Okay, and the higher bound of our confidence interval is -4 plus 1.645 multiplied by the confidence standard deviation, which is 5.2. Okay, so the confidence interval is all of our x's, all of our measurements will lie within this interval with 90% confidence. This is how we present data. We have 90% confidence that our data will lie between -12.554 and 4.554. Okay. This is the population language. This is what we call the population language. For the sample language, though, which is our case in general, we have to divide this by the square root of the number of data. But we don't really have, we are not given the number of data here, so we are just going to do the population route, not the sample route. So we are not calculating the standard error again. So you will be given a couple of data points, or you will record a couple of data points. You have to calculate the arithmetic mean, you have to calculate the standard deviation, and you will be given a confidence interval either by the lab instruction or by your TA. And you have to come here, calculate the z-score, or you can use an online calculator. It doesn't really matter to me. And then give us a confidence interval. Okay. What happens if the number of data points is less than 25, as I said? We are going to use a different method called the student T method. As far as you are concerned, the only difference here is that we have to calculate a new standard deviation called the sample standard deviation. The only difference between the two is that you divide your summation of the square of the deviations by the number of data points minus 1 instead of number of data points. See, this is how we calculate the standard deviation. This is how we calculate the sample standard deviation. The only difference is n and n minus 1. Okay, and we also have to calculate the t-score instead of z-score. Finding the t-score is even simple. You just have to know the number of data points you have in your case. So essentially, you come to this table to find the t-score. You will be given a confidence level, like 50%, 80%. This is called the two-wing confidence level, so you don't have to divide this by 2. You can just take the confidence level, come to this table, and then you have to calculate degrees of freedom, which is essentially your data points n minus 1. So this goes up to 25. So this table is good for 26 data points. So let's say we have 20 data points and we want the t-score for the 90% confidence. You find the degrees of freedom. 20 minus 1 is 19. So you come to this row, and this is the 90% confidence. So your t-score is going to be 1.729. Okay. Let's look at an example problem. We have 10 observations, so the number of data points is 10. Degrees of freedom is 10 minus 1, 9. The average voltage is 15 volts. Sample standard deviation is given 0.1 volts. And the uncertainty is 95%. So uncertainty level that you want to have is 95%. The degrees of freedom is 9. So you come here, 95%, degrees of freedom of 9. Your t-score is 2.262. See, 2.262 right here. So your delta, your uncertainty, which is t multiplied by your sample standard deviation. Here it uses sigma, but it should be s. 2.62 multiplied by 0.10 divided by the square root of the number of data points we have. So your uncertainty is plus and minus 0.0715 volts. This is how it represents the data. The estimate, the arithmetic mean, plus minus 0.00715, 95% confidence. So essentially, again, what this means is any measurement you make will lie within this data, within this interval, with 95% confidence. So you are 95% confident that any measurements you make will lie within this interval. Okay. So again, the general rule of thumb is when you have 25 or lower data points, you have to use a t-score method or a student t method. If you have more than 25 data points, you have to use the z-score method or the standard test method. Okay. So the question is, what happens if we actually have to make a couple of measurements, couple of different things? Let's say you are measuring the height and the depth and the thickness, the length, thickness, and depth. The 3 different measurements, and you have to make 20 measurements of each of these. But you are told to calculate the volume of these measurements. How does the uncertainty propagate to volume calculation? There are many different methods that we can use to find the uncertainty of the volume calculations. You can just add all of the uncertainties together. You cannot just take an average of all of the uncertainties. You have to use special types of different methods that are available. The methods that we want to talk about is called the Klein-McClintock method for propagation of uncertainty. So essentially what it says is, let's say you have 3 different or n different measurements. Again, length, depth, height, whatever. Right? You have to find a function that relates your, for example, volume to your height, depth, length, which is the function r, and you have to find the uncertainty of each measurement, uncertainty of length measurement, uncertainty of depth measurement, uncertainty of height measurement. So you have to find a function that relates your final calculated value. You have to find the uncertainty of each measurement, type of measurements. You have to take the derivative of your function with respect to that specific data. So you have to take the derivative of the volume function with respect to length, for example, multiply by the uncertainty of length measurements, take it to the power 2, add all of these together, and then take the square root of them. Might be a little too much. Let's go through this together by solving an example problem. Let's say you are measuring the height of a door and you get 2, which is your estimate, your mean, plus minus 0.03, your uncertainty. The door has a knob which is measured a small h, 0.88. Again, this is your estimate arithmetic mean of all of the measurements you have done, plus minus 0.04, which is your uncertainty of the knob measurements, height of the knob, from the knob to the ground, from the bottom of the door. Determine the uncertainty of the height Q from the doorknob to the top of the door. So our height H, which is the top of the door, is our x1 in the Klein-McClintock calculation. This 0.03 is our delta 1, or here W1. X2 is a small h, and W2 or delta 2 It's right here. What is the function? Q, which is our R in this equation, is equals to capital H minus a smaller than h. That is the function. So what is the derivative of this function with respect to capital H? Just 1. What is the derivative of Q with respect to small h? Negative 1. Okay. So how do we calculate the value for Q? How do we present the Q? Essentially, you have to subtract the estimate for the two heights, 2 minus 0.88. See right here, 1.2, 1.12. That is your new estimate. And then the uncertainty, just have to use this formula, the square root of partial r partial x1 multiplied by w1 to the power 2 plus partial r partial x2 multiplied by w2 to the power 2. Okay, you just have to plug those numbers in, and then your final uncertainty will become 0.01. Just there's a small mistake here. This has to be -1, but it doesn't really matter because we are taking this everything to the power 2. Okay. If you have trouble understanding how to do all of these calculations, I will be in class on Wednesday. This is next Wednesday. Next Wednesday, 22, January 22nd. I will be in class to answer any questions you might have. In the lab though, you will be given just a 1, 2, 3 cube. This is 1 inch by 2 inch by 3 inches cube. And a caliper. You just have to make 30 measurements of each side of the cube and calculate the volume with different confidence intervals. That will be it for the lab. Okay, that's it for lab 1. Please let me know if you have a question, or let your TA know if you have any question, and enjoy the rest of your day.